Welcome back to the third video for TEC 259 on Monday, February 22nd. In this video, I'm going to work out a calculation problem using several different modes of heat transfer. And then we'll also talk briefly about problem set number 11, which is the assignment for next time that has combined modes of heat transfer. I'll tell you ahead of time, the problem that we're going to solve together right now is there's a little bit of a curveball in it, all right? There's a little bit of a curveball that you'll see once you start the calculation on it. And there is that same curveball in problem set number 11, all right? So I could have made it completely trivial and straightforward, and you just calculate the resistances and put them in series and parallel, but there's a little bit of a curveball that you're going to see here that's not obvious when you just read the question, but when you start working through the problem, at some point you'll realize, oh, well, I'm not sure how to deal with that. So that's why I'm doing an example problem that has that same curveball in it. So follow along with this example problem and we'll talk through how to deal with that curveball that is going to show up in problem set number 11. So I'm going to switch over to the document camera. All right, here is an example problem that we will talk through. And it's a little bit contrived, but it'll work, and it's a good problem for us to work through. In fact, what you might want to do, what would be really good practice, after I talk through the problem, you might want to try to solve it yourself, and then come back and watch the video and compare what you did against what I did in my solution. So here's the problem. We've got some type of hot liquid. Maybe I'll say it's like hot cider. That sounds pretty good on a cold day. So we'll say it's like hot cider, and that hot cider is inside of a cylinder, like a wooden barrel. So hot cider inside of a wooden barrel, and that wooden barrel is inside of a room, and we're given the room dimensions. And just to make things a little bit easier for right now, we're going to say, unrealistically, that this room is at a vacuum. That way we don't have to deal with any ventilation, either natural convection or forced convection that might happen inside that room. So if it's a vacuum in here, then we know there's only one type of heat transfer that can happen between the walls of that barrel and the walls of the room, right? Okay, so we've got hot liquid inside this barrel, and the heat is going to transfer through the walls of the barrel, right? And then it's going to transfer from the outside exterior of the barrel to the walls of the room. All right, so that's basically the question. How much heat is going to transfer from the hot liquid that's inside the barrel to the walls of the room? How much heat transfer are we going to get? Okay, there's one more simplification that we're going to make for this problem. And that is that we're going to say that we know the temperature, not of the liquid, not the bulk fluid temperature of the hot cider, but instead we actually know the temperature of the inside walls of the barrel. All right, there's a big distinction there, all right? Because normally, if we just said that we knew the bulk fluid temperature, the average temperature of the hot fluid in here, well, you got to transfer the heat from the bulk fluid to the inside walls of the cylinder, right? What does that sound like? That's convection. So really you'd have, if this was a little bit more realistic, then what we would have is we'd have the hot fluid, we'd have convection from the hot fluid to the inside wall of the barrel. Then through the wall of the barrel, we'd have conduction. And then if this was more realistic, then we would have both radiation heat transfer from the outside wall of the barrel to the walls of the room, and we'd have convection from the walls of the barrel via natural convection or ventilation, forced convection, something from the walls of the barrel and then to the bulk air temperature, and then also from the bulk air temperature to the walls of the room. So we're simplifying this problem quite a bit by saying, all right, I actually know the temperature of the inside of the wall of the barrel. That eliminates this convection term here from the bulk fluid temperature to the interior wall. And I'm also going to say that the room is at a vacuum. Therefore, I don't have to deal with any convection outside the barrel. So all I've really got here is only two thermal resistances in this problem. I've got conduction from the inside of the wall to the outside wall of the barrel. And then I've got radiation from the outside wall of the barrel to the walls of the room. So that's it. That's all we've got. We also know all the parameters that are given here, though. We know the height of the walls in the room. We know the height of the wooden cylinder. They are 3 meters and 2 meters, respectively. We know the temperature of the inside wall of the wooden cylinder. It's 90 degrees Celsius. So go ahead and convert that to Kelvin right away. That way you don't forget to do that. And we know the temperature of the walls. That's given as 25 degrees Celsius, which is 298 Kelvin. We're given the thermal conductivity of the wood. We're given the emissivity of the wood, the emissivity of the room walls. We're given the dimensions. So we are told that R1 is the interior radius of the barrel, and that is 1 meter. And R2, which is the outer radius of the barrel, is 1.04 meters. So that tells you that the wall thickness is 40 millimeters or 4 centimeters. But we don't need that. We just need R1 and R2. So we're going to need to calculate the area of the cylinder, just like in the homework problem for today that was due today. It was pi times the diameter of the cylinder times the height of the cylinder. Because, you know what, it doesn't say here, but let's go ahead and assume that we will neglect heat transfer from the top and bottom of the barrel, just to make things easier, okay? So another simplification, we're only concerned with heat transfer from the sides of the barrel. That's going to be most of it. So let's just focus on that. So that's pi, that's the diameter. Be careful there. It's not the radius, but it's the diameter. In other words, R2 times 2 gives us 2.08 meters, and the height is 2 meters for the barrel. So our surface area around the sides of the barrel is 13.07 meters squared. That's an awfully big barrel, but that's okay. It'll work for now. The area of the walls, we'll need those two, that too. It's the side length times the height times, there's 4 of them. So that's the total surface area of all the walls added together. So the delta T, that might be useful. I went ahead and calculated it here. The difference from T1 to T2, that is 65 Kelvin. So that's the difference from the inside wall temperature to the exterior the room wall temperature. So the next thing we should do once we understand the problem is to draw the thermal resistance. And that would look like this, where I've got T1, that is the inside of the barrel, inside wall of the barrel. And T2 is the temperature of the rooms of the wall. So like I said before, I've only got 2 resistances here. We've only got conduction through the wall of the barrel, and then we've got radiation from the outside wall of the barrel to the walls of the room. That's it. That's all we got. So we know how to do this. We're just going to combine these resistances in series. So we got to calculate these resistances, and then they're in series. So we're just going to add them together, right? We are. That's true. All right. But you are going to notice that there is, as I said, kind of a curveball in this problem, and you can see it already if you really think carefully about what is going to be involved in calculating this thermal resistance and calculating this thermal resistance. All right, so we're going to go through this in a second, but I just want to give you a preface here. So the resistance for conduction, what's that? It's L divided by Ka. Actually, no. That's that would be true if it was a planar wall, but it's not a planar wall, is it? All right. So we got the natural log of R2 divided by R1 times 2 pi Lk. That's what the thermal resistance here is going to be. Okay. So we know R2, we know R1, 2 pi is a constant, L is the height of the barrel, K is the conductivity of the wood. So there's no problem there. We know all of those things. So I don't foresee any problem calculating this resistance right here. Okay. What about this resistance right here? All right, so it's our radiation. So we're going to have our surface resistances, our space resistances, first of all, right? So the surface resistance involves the emissivity and the area. But I know all of that. I know the emissivities and I know the area of both of these things. So that's not going to be a problem. The space resistance, well, now that's going to include the area and the view factor, but that's not going to be a problem either because I know the areas and the view factor. Well, look, this is entirely inside the room. So the view factor here is going to be 1, just like we had in the homework that was due today. The view factor is going to be 1. So that's no problem either. Calculating the surface resistances and the space resistances, no problem. But the next step, think about the next step. We take our surface plus space resistance, add those together, and we combine that into R rad total. But what does R rad total include? R rad total includes the temperature of the body that is radiating and the temperature of the body that is receiving the radiation, right? And up till now, that's been no problem. We've known that. But here, that's a problem because we don't know the temperature right here. In other words, we don't know the temperature at the outside wall of the barrel. We only know the temperature at the inside wall of the barrel. That's T1. But we don't know this temperature right here. So that's a problem because it's not going to allow us to directly calculate the radiation rad total resistant, R rad total, for the total radiation thermal resistance. All right, so we're gonna have to figure out some way to deal with that. And basically the way that you deal with that is via a sort of kind of iterative or kind of guess and check process. And I'll talk you through how to do that. But that's basically what we got to do. I just want to show you that right off the bat. There's a problem with this. There's a problem calculating this because we don't know the temperature of the body that is being radiated. We don't know, radiating. We don't know the temperature of the body that is doing the radiating. That is the outside temperature of the barrel. So we have to do a little bit of an iterative or guess and check method. And we'll talk through that in just a couple of minutes. All right. But first, let's calculate what we do know, what we can. So like I said, the conduction thermal resistance is pretty straightforward. We know all these values. We've got the natural log of R2 divided by R1 divided by 2 pi Lk. R2 is 1.04 meters. R1 is 1.0 meters. The meters cancel out. 2 pi, then we plug in 2 meters for L, and K is 0.15 watts per meter per degree Celsius. So a lot of those units cancel out. The meters all cancel out, and we're left with 0.02081 degrees Celsius per watt, which is really the same units as Kelvin per watt because a delta T of 1 Celsius is the same as a delta T of 1 Kelvin. So you could actually have either one of these units. For radiation, we can go ahead and calculate our surface and our space resistances because we have all of those. We have our emissivities and we have our areas and our view factors. So here's our surface resistance from the outside of the barrel. 1 minus the emissivity of the wood divided by the area of the wood times the emissivity of the wood. So we get 1 minus 0.9 divided by the area of the wood, which is 13.07 meters squared, times the emissivity of the wood again, which was 0.9. And we get a surface resistance at the wood outside of the barrel of 0.008501 1 over meter squared. Then we have our space resistance from the outside of the barrel to the room walls. We got 1 divided by the area of the wood times the view factor. And the area of the wood, once again, is 13.07 meters squared. The view factor is 1 because any radiation that is emitted from the wall of the barrel has nowhere else to go. It's got to go in a straight line, so it has nowhere else to go. It's got to go to the walls of the room. So the view factor is 1. So I plug those in and I get 0.076511 1 over meters squared. Then we have the surface resistance of the walls. So it's 1 minus the emissivity of the walls divided by the area of the walls times the emissivity of the walls. So we plug in numbers for that. We get 1 minus 0.8 divided by 120 meters squared times 0.8. And you get 0.002083 1 over meter squared. So now it's no problem to add these up. We can add up our surface plus space resistances from here to here, from here to here, from here to here. And we get 0.087095 1 over meter squared. So that's great that we have the surface plus space resistance. That's important, and we have that now. But what you will want to do in the next step is calculate R rad total, right? That's the total thermal resistance for radiation. And when you plug that in here, here's the equation for R rad total. You'll see, this is where you'll see there's a problem, or you should recognize that there's a problem. Because in the numerator here of R rad total, we have our surface plus space resistance. That's no problem. Take that from up here down to here. But down in the denominator, we have Stefan Boltzmann constant times the quantity T sub W, where T sub W is the outside temperature of that wood. That's the body that's radiating. We square that temperature plus T2 squared. That's the temperature of the body that's being radiated. And then we take that times the quantity T sub W, that's whatever is radiating, plus T2, whatever is being radiated. All right, and the problem is that we don't know the temperature of the body that is radiating, because that is the temperature of the outside wall of the wood barrel. So that's a problem. We can't directly calculate our rad total. So what we have to do, and it says this up here, we have to guess. We have to guess what it is. And then once we make that guess, then we can go back and we can do an iterative check. We can check what that temperature difference across the wood barrel, the walls of the wood barrel would be based on our assumption. All right, so let's go ahead and do it. I think it'll make sense as we're doing this. So we don't know, we can't calculate R rad total, because we don't know the temperature of the outside of the wooden cylinder. That's the temperature of the body that is doing the radiating. So I'm going to call this T sub W for temperature of the wood. And I'm going to make a guess. And my initial guess is that the temperature of the wood, that's the outside temperature of the barrel, is 60 degrees Celsius. So it's a wild guess. I mean, I literally just made that up. That's just a wild guess. 60 Celsius is 333 Kelvin, which would make the delta T across the wood of the barrel equal to 30 degrees. And the way I got that was, we know from the givens of the problem, we know that 90 degrees is the temperature at the inside of the wood. And now I'm guessing that the outside temperature of the barrel is 60 degrees Celsius. So if that's right, this is what we're going to check. If that's right, that would make the temperature difference across the wood of the barrel 30 degrees Celsius. So keep that in mind, and then let's proceed with the problem, assuming that T sub W is 333 Kelvin. Okay, so we're going to proceed. So I'm going to plug in values here for T sub W and for T2. T sub W is 333 Kelvin. T sub 2 is the temperature of the room walls, which is 298 Kelvin. So I plug those numbers in and I get a R rad total of 0.012190 Kelvin per watt. All right, so that's R rad total. Now I can say, all right, I know, or at least I have an assumption for what this value is. So I can find my total thermal resistance by adding the conduction thermal resistance to it. So that's what I'm doing down here in the next step. Our total for this problem equals the conduction thermal resistance plus R rad total. I'm taking the conduction thermal resistance from up here where we calculated that. So I'm adding that to our rad total that we just calculated based on our assumption. And I would get a R total of 0.033000 Kelvin per watt. All right, so that's the total resistance. The next thing I'm going to do is I'm going to check the validity of that assumption that I made earlier, where I said the outside temperature of the wood is 60 degrees Celsius. So the way I'm going to check that is by calculating the delta T across the wood. I'm going to tell you how I'm going to check that assumption that I made, but first let me make a quick explanation by comparing this to something that I actually teach about in a different class, but I'm just going to simplify it here. So think about electrical circuits. Let's say I have a voltage of, let's say 10 volts. And let's say I have two resistances. And let's say those resistances are both equal to 100 ohms. All right, so I have 10 volts applied across this circuit, and I have two resistors. They're both 100 ohms. So can you tell me, just based on your intuition, what do you think is the voltage drop from here to here compared to the voltage drop from here to here? Well, they're both 100 ohms, so they're going to have the exact same voltage drop. Half of that voltage is going to be dropped from here to here, and half of the applied voltage will be dropped from here to here. All right, so I think that's kind of intuitive. Now let me make just a slight modification. Let's say it's still 10 volts, and I've still got two resistors, but now let's say R1 equals, let's say 60 ohms, and let's say R2 equals 40 ohms. All right, so I've got two resistances. One is 60 ohms, one is 40 ohms. Can you tell me the voltage drop from here to here compared to the voltage drop from here to here? Well, if R1 has a higher resistance than R2, then more of this voltage is going to be dropped across R1 than across R2. All right, so the voltage drop is actually proportional to this resistance as a fraction of the total resistance. So there's actually an equation for this. It's called the voltage divider. You don't have to know this because this class is not yet about electrical circuits. But the voltage drop across resistor 1 is equal to the ratio of R1 divided by R total, that ratio times V total. So it kind of makes sense. If 60% of the resistance is right here, then 60% of the voltage drop is going to happen from here to here. All right. If 40% of the total resistance is right here in R2, then 40% of the voltage drop is going to happen across R2 from here to here. This works for components that are in series like this. All right. So that may not be very applicable to this class, but remember, voltage is basically the same as temperature. It's analogous to temperature. So if I have a thermal resistance network like this, and let's say my delta T equals, let's say 10 degrees Celsius, just to keep it analogous to the voltage here. So my delta T is 10 degrees Celsius, and don't even worry about the units right here, but let's say this has a resistance of 6x, whatever x is, are the units for our thermal resistance, and this has a resistance of 4x. Where's most of the temperature drop going to happen? Well, just like before up here, most of the temperature drop is going to happen across the component with the largest resistance. So what that means is that from here to here, I'm going to get 6/10 of the total voltage drop, which actually means temperature here. So from here to here, I'm going to get 6/10 of the total temperature drop, which in this case, 6/10 of 10 degrees is 6 degrees Celsius. And from here to here, I'm going to get 4/10 of the total temperature drop, which means 4 degrees Celsius from here to here. So this is the principle that we're going to use to check our work. All right. It's called voltage divider when it's applied to the electrical domain. It doesn't really have a name when it's applied to the temperature domain, but that's what we're going to use. We're going to say, all right, I assumed a temperature right here. That's what I did in this problem. I assumed a temperature. So with that assumed temperature, I can calculate the assumed resistance right here. So if I calculate this assumed resistance, and then I calculate with that number what is the actual temperature drop from here to here, I compare that against my assumption, and I can modify it and change the assumption in iterative steps. All right, so that's what we're going to do. Let's talk through it, because I think it's easier to do it than it is to explain it honestly. So switching back to the problem at hand, we made an assumption for what the temperature of the outside of the barrel was. That was 60 degrees Celsius, which would make the delta T across the walls of the barrel 30 degrees Celsius. Then we used that information to calculate R rad total, which we used to calculate R total for the whole problem. And what we're going to do with that, once we have R total, we're going to find out what is the delta T across the wood barrel and compare that delta T with our assumed delta T that we assumed was 30 degrees Celsius. All right, so those are the two that we're going to compare. We're going to compare that delta T, that temperature difference across the barrel using this information, R total, and we're going to compare that to the assumed delta T based on our assumed temperature, which was 30 degrees Celsius. All right, so that's what we're going to do. So the way we can do that is by comparing our resistance, our thermal resistance across the wood. So that was the conduction resistance, right? So our conduction resistance was 0.02081, and our total resistance was 0.033000. So if we take a ratio of that to that, that should be proportional to the delta T. That should be proportional to the temperature drop across the barrel, just the barrel part. All right, so this is the thermal resistance for conduction through the barrel. This is the total resistance for the problem based on our assumption for the temperature of the outside of the barrel. And I take that times my total delta T across the whole problem, which I do know. I know that. That's the temperature on the inside of the barrel compared to the temperature on the room walls. I do know that. So based on those calculations, that would tell me that the temperature difference across the wood is equal to 40.99 Kelvin, or 40.99 degrees Celsius. But that doesn't match up with what our assumption told us. We assumed that the outside of the barrel was at 60 degrees Celsius, which would make for a delta T across the wood of the barrel of 30 degrees Celsius. So these numbers don't match up, right? So clearly we were a little bit off. We were not correct. So were we too high or too low? Well, our assumption was the temperature drop was 30 degrees Celsius from the inside to the outside of the barrel, but actually we calculated 40.99 degrees Celsius. So actually the outside temperature of the barrel is going to be lower than what we assumed because our delta T is higher here. So there's more of a temperature drop from the inside to the outside of the barrel than we guessed. That's what that tells us. So we need to guess again, and we'll try to get closer. When these two things match up, then we know we're really close and we've got the solution to the problem. So let's guess again. And instead of 60 degrees Celsius, I'm going to guess that the outside wall of the barrel is only 50 degrees Celsius, which is 323 Kelvin, which, if it's correct, that would make the delta T across the walls of the barrel equal to 9 degrees minus 50 degrees, which is 40 degrees Celsius. Okay. So now we go through the same calculations that we just did, not all of them, but now we just have to calculate R rad total again. All right, so don't calculate the surface and space resistance again. That's the same. That's not going to change. The only thing that's changing is our temperature for the wall of the barrel right here and right here. So I plug in for the Stefan Boltzmann constant right here. This is the temperature, the new assumed temperature of the outside of the barrel. This is the temperature of the walls. This also is the temperature of the outside of the barrel. This is the temperature of the walls. And now my new RRAD total, based on that estimate, is 0.012807 Kelvin per watt. So if that's my new RRAD total, I can calculate a new R total for the whole problem. I just add this plus the conduction resistance, which I do know, and then that would give me a total problem thermal resistance of 0.033617 Kelvin per watt. And then once again, I do the same thing that I did up here. I take the thermal resistance for conduction through the barrel and compare that to the total thermal resistance in the problem. That's my ratio. I'm taking that times my total delta T in the problem to find what now is the delta T just across the barrel. All right, so when I do that calculation, I get 40.24 Kelvin. Guess what? That's really close. Using that assumption, I would get a delta T across the wood of 40.24 Kelvin. And my assumption, which was a wall temperature of 50 degrees Celsius, that would give me a delta T across the wood of 40 degrees Celsius. So that's really, really close. That's good enough, honestly. If you're within 1 degree Celsius, that's definitely good enough. But I'm going to do it one more time, just kind of for clarity's sake and to show how we're doing this. So what it says here, our second guess was a delta T across the wood of 40 degrees Celsius. So that is very close to that. So we're really close. So that's definitely close enough. We could stop here. We could use that value for our total to calculate Q dot. But just for fun and to show another demonstration, I'm going to do it again. I'm going to try and get even closer. So now what I'm going to do is make another guess. And we see that the delta T that we calculated here was actually still a little bit higher than our assumption. So I'm going to revise my temperature of the wood a little bit more. I'm going to decrease it a little bit more by 0.2. So now I'm going to assume that the temperature of the wood outside of the barrel is 49.8 degrees Celsius, which is 322.8 Kelvin, which, if it's true, would make delta T across the wood equal to 40.2 degrees Celsius. So now I go through these 3 steps again. I recalculate our rad total, not changing surface and space resistance. That stays the same as it did in the previous 2 times I did this. Not changing the Stefan-Boltzmann constant. The only thing I'm changing is the temperature of the wood right here and right here. So this is the temperature of the wood squared. That's the temperature of the walls squared. That's the temperature of the wood. That's the temperature of the walls. So now, based on my updated assumption, our rad total is 0.012820 Kelvin per watt. I add that to my conduction thermal resistance to get a new updated estimate for total resistance, which is 0.03363 Kelvin per watt. And now I can check, once again, how valid was that assumption? Well, I take my conduction resistance, divide by the total resistance. That's the ratio of the resistances. And then this is my total delta T in the problem, which would give me a delta T across the wood of 40.22 Kelvin, which is really close to my 40.2 degrees Celsius delta T across the wood. So these are really, really close. So that's a really good assumption, a really good estimate. It's only 0.02 degrees Celsius or 0.02 Kelvin different. So it's really close. And we can use now this number for our total in our calculation. So the rest is really easy. The rest, we just plug that value of our total into our basic heat transfer equation. T1 minus T2, that's the temperature inside the barrel to the temperature of the walls. So that is 65 Kelvin. And now we just take this total for thermal resistance down to here, and we plug that in, and we get 1,932.8 watts, which is about 1.9328 kilowatts. I know that kind of seems like a lot, that iterative guess and check method seems like a lot to deal with at first. And the first time you do it, it kind of is. It takes a little while. But it really is not that bad once you kind of figure out what it is that you're doing. It's just kind of hard to conceptualize what it is exactly that you're guessing and comparing against. But once you work through that, then I think that it'll become fairly straightforward. All right, so let's take a look at problem set number 11. That is the homework assignment that will be due next time. So here's problem set number 11, and it's pretty similar to the example that we just talked through, and that was intentional on my part. So in this case, we've got a cylindrical boiler inside the enclosed room, and the fluid inside the boiler is at 300 degrees Celsius. And we're given that the convective heat transfer coefficient between the fluid in the boiler and the interior surface of the boiler is 50 watts per meter squared per degree Celsius. So that's H. All right, so I'm actually kind of doing you a favor here by saying that you don't have to calculate here, in this case, from here to here, you don't have to calculate that Reynolds number or that Nusselt number. You've already got H. So I'm giving you H with which you can calculate the convection thermal resistance. All right, so that is the resistance from the bulk fluid temperature to the interior of the boiler wall, the interior wall of the boiler. All right. Then the inside diameter of the boiler is 3 meters. Remember, that's diameter. All right, so careful there. Diameter of the boiler is 3 meters. And the steel boiler walls are 4 centimeters thick. So this wall right here is 4 centimeters thick. That's 0.04 meters thick. And the insulation that's wrapped around the boiler is 10 centimeters thick. So that's this second layer right here. That is 10 centimeters, which is 0.1 meters. And we're told the room is 15 meters square. That means it's 15 meters by 15 meters. So the room is a square with a wall length being 15 meters. And the boiler is 3 meters tall. The room walls are 5 meters tall. And we're told that there is ventilation, and the air and the walls of the room are both at 30 degrees Celsius. So the bulk fluid temperature of the air in here is 30 degrees Celsius, and the temperature of the walls is 30 degrees Celsius. We're told the average air velocity around the outside of the boiler is 0.5 meters per second. So there's fluid, there's air is a fluid. There's fluid around this boiler, and that air is flowing with a velocity of 0.5 meters per second. Ignore the heat transfer from the top and bottom surfaces of the boiler and neglect the heat transfer to the ceiling and the floor of the room, just to simplify the problem a little bit. And calculate the total rate of heat transfer from the fluid inside the boiler. We're given all these different parameters right here. So I'll help you out a little bit. I'll get you started because this is a fairly involved problem. There's a fair number of calculations here. So what do we got? We got our bulk fluid temperature. Let's call that T1. So here's T1. And so the heat is going to transfer from T1, that's inside the boiler. It's going to transfer ultimately out here to the ambient environment. And both the air and the walls are at 30 degrees Celsius, which is T2, right? So over here, I'm not going to draw it yet, but we're going to have T2, which is going to be 30 degrees Celsius because that's the temperature of the air and the walls. But as the heat is going through there, what does it have to go through first? Well, first it has to convect from the inside of the boiler to the inside boiler wall. That's the first thing it has to do. So our first thermal resistance is a convection resistance. So I'll write R sub CO in V. And in this case, it's pretty nice because you're actually given H here. You're given the convective heat transfer coefficient. So remember, R for convection is 1 over HA, and you're already given H. So you don't have to go through and calculate the Reynolds number and the Nusselt number here. You can calculate this very easily, very quickly. You got to know H and you got to know A, the interior area, the inside area of the wall. Okay, so that's the first resistance. What's next? So now we're here. Now all of that thermal energy is going to have to pass through this layer right here, which is steel. So because all of the thermal energy has no choice but to pass through this layer, it's got to be in series with this convection term. So our next thermal resistance is going to be thermal resistance of the steel, right? So that gets us through the steel. And remember, for this one, you're going to have the thermal resistance is equal to the natural log of R2 divided by R1. Remember, those are radiuses, not diameters. So calculate those radii. Natural log of R2 divided by R1 divided by 2 pi Lk, where L is the height of the boiler in this case, and K is the thermal conductivity of the steel in this case. Then we're at the outside of the steel. Next, we have to go through the insulation. And any heat that goes through the steel has no choice but to also pass through the insulation. So it's going to be in series. So this is going to be the resistance of the insulation layer. Once again, it's going to be natural log of R, in this case, R3. Be careful here. Your outside radius of the insulation is not the same as the outside radius of the steel. So be careful about the radii that you choose here, but it's going to be natural log of, in this case, R3 divided by R2 divided by 2 pi Lk. And L is going to be the same as the boiler. K is going to be the thermal conductivity of the insulation. All right, that gets us to the outside of the boiler, the outside of the insulation of the boiler. Now what's going to happen? Now we're going to have thermal energy that can be transferred via convection because we've got a fluid flowing over this boiler. And it's also going to be transferred via radiation. Those are two independent modes of heat transfer that can both be happening at the same time. So does that sound like series or parallel? Hopefully it sounds like parallel. So I've actually got two different modes that can happen at the same time. I've got R convection and I've got R for radiation. And remember, we call the total radiation resistance R rad total. R rad total. All right, that says R rad total. Okay, and then they both go to a final temperature T2 of 30 degrees Celsius because the air is 30 degrees Celsius and the walls of the room are 30 degrees Celsius. Okay, so how are we going to do this? Well, our convection, we're not given H here like we were for this convection term. So we got to calculate that. So this time you will have to calculate the Reynolds number. You'll have to use the relationships for the Nusselt number. You'll have to calculate H and then calculate 1 over HA. All right, so for this one, you will have to calculate the convection thermal resistance. And then what about this one? This is R rad total, but you notice that there is a problem here. Not really a problem. It's a curveball, not really a problem. But it's similar to our example problem we just did in that you can calculate the surface resistances and the space resistance, but you can't calculate R rad total because you don't know this temperature right here. You don't know the temperature at that node. And R rad total needs the temperature of the body that's emitting as well as the temperature of the body that is being emitted to. That is receiving the radiation. All right. So you're going to have to make a guess. You're going to have to guess what this is. And using that guess, calculate R rad total. And then using that guess, calculate R total and compare your assumed delta T from here to here against what you calculate your delta T is based on R total. All right. Using the fraction of this resistance from here to here, this resistance from here to here, compared to the total resistance and these total delta T's, all right, just like we did in the example problem. So I don't want you to spend, an infinite amount of time on this. So I will tell you, make 3 guesses, all right? So if you make 3 guesses, just like I did on the example problem, I made 3 guesses. And it turned out on the example problem, I was really, really close after 3 guesses. But I don't care how close you are. I want you to do 3 guesses, 3 iterative guesses to get an understanding of how to do this type of problem. and you can call that good. Whatever you're at after 3 guesses, that will be close enough for our purposes in this problem. All right. So I think that's a pretty good hint. All of this is a pretty good hint to get you started on this problem. This is the only problem for problem set number 11. It's only one problem, but it's fairly involved. It's probably the most involved problem set that we've had in this class up to this point. So take a good solid stab at it, give it your best shot, and we will talk about it at the beginning of class next time. So that will wrap things up for today. I will see you next time when we will talk about a review of problem set number 11, and then also we'll talk about more about heat exchangers next time. So have a good week, and I'll see you next time.